So now let's move on to our high pass filter. So here we have another simple circuit. I've just replaced our capacitor for an inductor. And remember, whenever we're doing this type of analysis, the first thing we want to do is we want to transform this circuit to our frequency domain. So we want to go to our frequency domain, and so we do that by changing our voltages into phasors and by changing our resistances, inductances, capacitances into impedances. So now we have our input phasor is going to be VI, capital V, lowercase I. Our V out is capital V, lowercase o. And our impedance for our resistor we know is just equal to the resistor value. Our impedance for the inductor is dependent on frequency. We know it is J omega L. And so we've not analyzed this circuit before, so let's go sort of back to our basics in order to find our transfer function. So remember, our transfer function in general is equal to output over input. So we want some expression that relates our output voltage to our input voltage. So what we can do is we can use voltage division. So using voltage division, we can say that our output voltage is equal to our input voltage times the impedance of our inductor, J omega L, divided by the sum of the two impedances in series. So R plus J omega L. And so I'm going to adjust this a little bit so that we only have a 1 in the numerator. That's just going to make things a little bit easier later on. So dividing numerator and denominator by J omega L, I get 1. And I'm going to have, from the right term in the denominator, I'm going to have 1. I'm going to move it over to the left. And then dividing that R by J omega L, we just have R divided by J omega L. Okay, so I've left out, so we have this is multiplied by VI. So of course now we could just divide both sides by VI to find our transfer function, H of J omega, which again I'll write explicitly as V out over VI. And so we have that that is equal to 1 divided by 1. We had plus R over J omega L, but remember we can move that J to the numerator, and we could say that's minus J times R over omega L. So we get that expression for our transfer function. So of course we could write an expression for the magnitude of this transfer function. So magnitude of H of J omega. In the numerator, that's just going to remain a 1. In the denominator, we're going to have square root of 1 squared, which is just 1, plus the square root of this negative R over omega L squared. And so I think in the notes I've not included that negative sign because it's being squared, so ultimately it's not really going to have any effect. Okay, so this is our magnitude of our transfer function. So now we can consider our general behavior by considering our extreme cases as we've done before. So general behavior from extreme cases. Okay, and so this is always a good place to start if we don't necessarily know what a circuit is doing. We can say, well, let's consider extreme cases, omega equals 0 and omega equals infinity, or omega goes towards infinity, basically a really large number. So what we can see here is if we have omega equals 0 in this magnitude equation, then we're going to have an infinite term in our denominator. So if our denominator is really large, that means our overall transfer function is going to be 0. So this is going to mean that our magnitude of H of J omega is equal to 0. So on the other hand, so again, still focusing on this omega here, if this omega is getting really large, then this whole term is going to be very small, and essentially it's going to go away, and we'll just be left with 1 divided by 1 for our transfer function, giving us a magnitude of H of J omega equal to 1. So this basic behavior we know is behavior for a high pass filter. So higher frequencies are allowed to pass through. They get multiplied by 1 from our transfer function. Lower frequencies get multiplied by 0, so they do not get passed. So now what we want to do is we can find our cutoff frequency similar to how we did previously. So we want to find our cutoff frequency. And so our cutoff frequency, remember, is at omega c. And so based on the arguments we made in the previous video, what we can do is we can take the magnitude of this transfer function at a value of omega equals omega c, and we know that's going to be equal to 1 over root 2. The reason we do 1 over root 2 is because we're talking about voltages here. And so if it's a half power band, then it's 1 over root 2 for our current and voltage. So the transfer function is 1 over root 2. We set that equal to the magnitude expression that we had above. So we had 1 divided by the square root of 1 plus a negative r over omega c L squared. And so again, in the notes, I don't have this negative sign because with the squared it goes away. For completeness, I've included it here. So if we solve this for that omega c, that corner frequency, what we get is that omega c is equal to r over L. Just like with our previous video, we want to keep in mind that this is only for this particular circuit. So this is for this particular circuit. So this isn't a general equation for high-pass filters. So again, that's only for this circuit right here. Okay, so now what we can do is we can sort of plot this response, and let's do what we did with our low pass and sort of overlay that with our ideal response. So versus frequency, we're plotting the magnitude of our transfer function, and we know our key frequency is going to be this omega c value, and our key values of magnitude are 1 and 1 over root 2. So let's do our ideal first, and that's kind of going to give us a baseline. So we know our ideal is 0 for less than omega c and 1 for all values above omega c. So this is our ideal case. Now for our actual case, we know that at this value of omega c, that's our half power point, which corresponds to a voltage or current magnitude of 1 over root 2, which again is about 0.7. So what we have then is we have something that has more of some curvature to it, and is going to look something like this. And so like we saw with our low pass filter, the difference between this sort of top corner of our ideal filter and where we're actually at omega c is going to be a value of 3 decibels. So that's again why we call this omega c our 3 dB frequency. So let me come back here and explicitly label this as our actual curve. And so in this case, we found our omega c is equal to r over L. So again, by adjusting resistance and or inductor values, we can set that omega c where we want it to be. But again, keep in mind as we change that configuration, we're changing that cutoff frequency. And we can add more components again to sort of make this actual curve, this red curve, approximate better our ideal curve. But right now we're just looking at our most simple case. So one thing to consider sort of in lines with what we talked about with our previous circuit as well is we can ask ourselves, what if we defined our output voltage instead of being across our inductor, what if we came up here and we defined it across our resistor? And so of course what we would see is that we would be changing the type of filter, and instead we're going to have a low pass filter with the same omega c. The point there again is just it's very important to note, to be aware of the fact that filter behavior is dependent on where our outputs and inputs are defined.